Welcome to Extreme Makeover NGSS edition, and this is the mystery of the Oasis in the desert. This particular activity is really targeting the high school 3-course model, which is trying to explore a synergy between Earth and space science phenomena and mechanisms from life and physical science, where we're really using these Earth and space science phenomena to motivate in-depth study of mechanisms from the life and physical science. And in turn, we're hoping to really use those understandings to help our understanding of Earth science mechanisms in return. So how does this work in a living Earth classroom? We're going to look at an example called The Mystery of the Oasis in the Desert. Our activity begins with me asking you to picture a desert. What do you see? What are the colors like? What is the vegetation like? And in particular, what we're going to be doing in a moment is we're going to be looking at an aerial photograph looking down on the desert. And I want to have you picture what that might look like and how that might be different. What are the colors? What are the shapes that you're going to see? All right, you got that in your head? So let's go ahead and jump on in and look at that. Here is a Google Maps image near the the city of Tucson here, which you can see looks a little bit different than the colors in the surrounding deserts and mountains here, Saguaro National Park and a local park here. Are those colors what you expected? Well, now we're going to zoom in on this area here of the desert, a little bit more of the raw open desert. And here's what that looks like. Wow. I'm noticing some interesting patterns in here that I wasn't necessarily expecting. In this particular case, I can see all these little lines coming and connecting together here. These are river channels, and you can see that there's vegetation that's growing in them that makes them a little bit more green. We're going to zoom in into this area up here in particular and try and figure out what's going on there. Whoa. Well, that's a little bit unexpected. All the areas around in here, in between these green patches, are kind of what I expected, but these dark, beautiful, rich green areas, what's causing those? Why are there little oases in the deserts? And that's the mystery that we're going to be trying to explain in this activity. In order to do that, we're actually going to zoom on in and take a virtual field trip via YouTube.
I'm in the flat bottom land here, kind of a penny plain in the Sonora Desert, and there's not much fertility around. It's pretty sparse vegetation actually. Then you see this obvious event starts to happen. The trees get green and big and the vegetation gets really lush. And this is something you need to really understand. We go into a complete cover of vegetation. This is leaf amaranth, what they call in the Caribbean callaloo. And it's way taller than my head in places. And obviously indicating it's extremely fertile in here and very well watered. The trees are very lush. Nobody planted these planted themselves. And it's green and shaded. It's very pleasant in here actually. It's a very pleasant environment. Wow. It's not every day that you see a scene like this, an oasis of lush verdant green created by nature. Outside, there's a hot, dry, dusty desert. In here, you couldn't believe you're in a desert. This is all green, lush and fertile and beautifully shaded and cool.
So we have this fascinating observation now in great detail that outside the oasis it's brown and inside the oasis it's green. And we want to figure out what's causing these green spots and why are they so different from their surroundings. I want you to, by yourself, come up with several possible ideas and then brainstorm with your partner as well. With those ideas in mind, I want you to pick one of them and come up with a full model that explains why the plants are green and lush in those certain spots in the desert and why it's brown outside. Now, I've given you an illustration of an example of a model. And within NGSS, we're talking about a model. We aren't usually talking about like a 3D diorama of things. We're talking about often a picture or a diagram that shows how matter and energy move around within a system, the interactions within a system. And so I want to make sure that your model looks like this one in the sense that it tracks the cycling of matter within the system. Now this particular graphic shows both energy and matter. We're going to focus in on just the matter here, and you can imagine that matter would probably involve water. After doing this a number of times, you'll get a range of different models from different student groups. They might look like this here, where there's an aquifer and an impermeable layer. Maybe your students don't know enough about that, so they just draw a tree. Maybe they don't know what to call it, but they drew this dark brown stuff here. Maybe they know that there's groundwater and they've got something that looks like this with dirt and other dirt. And this is our starting point model. There are going to be some that have similarities, some that have differences. We'll go around and whip around the room and have each person give us a couple moments to talk about what their model includes and why they think there's green spots in some places and not in others. Now this is a commentary that allows us to jump off into one of the cross-cutting concepts of systems. Now as teachers, I'll give you a little bit of a background on it, but we might use this opportunity to actually introduce some key concepts about systems to our students, just like I'm doing here. Now a system, we think about a system and it has a boundary. We have to choose what goes inside and outside the system. So I've chosen here to show you a person system, and this comes from our middle school chapter of the framework, so you may or may not have seen it. Then within that system, there are different components, maybe cells and organs, tissues. There might be energy that's one of the components that you could think about. And then there are ways that those different components interact. Different processes that allow those different pieces to interact, like digestion or cellular respiration, circulation, moving matter or energy from one component to another. We also know that the human system is not going to survive by itself. It's got things that it brings in and stuff that it sends out, inputs and outputs like every other system. And when you take all four of these things together, you end up with something that gives the entire system properties. So your body has a certain temperature, and that's the sum total of all of these interactions in your system. Or your personality. You can't break it down into one individual part of you. That's a complete interaction between all of them that makes you special. So with the system that you drew, what were your system boundaries? What did you choose to include or not include? And if I go back here, none of these seem to include anything about life almost at all. They don't really include much about birds or animals. Did we need to? Are those outside our system boundaries? What about the components of the system? This one has them labeled in different colors as dirt and other dirt. This one has a brown thing. It has some CO2 and oxygen and water flowing around. This one here shows drops of water going into an aquifer. These are all the different components that are there that we have to trace. And did you label the relationship between the components? Our simple naive person here drew a tree and some brown stuff that represents soil, but didn't really talk about how those are related. Even this example here, we have a bunch of different parts, but we don't know exactly how they're related or how they're exchanging matter. This diagram up in the corner does show some examples of interactions, as does this one here. So these are the types of things that will allow us to start introducing different aspects of systems, the cross-cutting concept, to our students. And we might want to focus in on just one of them at a time, just one of them for this particular activity, because the understanding of systems is something that needs to develop over the course of years' worth of K-12 NGSS. So now, you've got a couple different models in your class, and some of them look similar, and some of them are completely different. Is one of them right? Is one of them wrong? Is there a right answer? Well, I will tell you this. There is a right answer in the sense that there's something that's causing some spots to be green and some spots not to be green. We're trying to figure out what that something is. So there's a right answer, But right now we don't have enough information to know which of our possible explanations, which of our possible models is the best model, the one that actually works. We might find some information that rules out certain models, or some information that is evidence that supports certain models. So at this point, we might have a lot of unanswered questions. And I want to give my students an opportunity to ask those questions. Special curricular space set aside for them to do that. So what questions do you have that remain about this mystery? And write down as many questions as you can at this point. It's a free-for-all brainstorm of lots of questions. I have them write down on Post-it notes, and then with those I introduce a way to categorize questions. I like to think about 4 different levels of questions here. We start in the upper left with simple, unbridled curiosity. This is a wonderful type of question. We love students expressing their curiosity. We're trying within NGSS, within the science and engineering practice of asking questions, though, to go beyond simple, unbridled curiosity and take their questions to another level. And so this other part of the diagram represents some ways that we could do that. Let's say that we have a question that demonstrates that we needed certain knowledge to ask that question. I'll show you some examples in a moment. That might be one thing that we could do. Another type of question that we could do is a question that asks some sort of testable, investigatable question. And then the optimal scientific question might actually be both investigatable and demonstrate some knowledge. So let's look at what these mean in real life. So here's an example in the upper left. Why is it green there? I have that question. There's nothing wrong with that question. And it falls within the simple, unbridled curiosity. And it's a great starting point question. But we want to go further. How about this one down here? Is there a pipe there that waters these areas? Could you investigate that? Definitely. We could go there. We could dig around. We could use Google Maps and try and see if we could see it. Definitely investigatable. But that particular question doesn't actually require much knowledge to ask. At the high school level, our students, any high school student, regardless of how much science they knew, might be able to ask that question. So that one isn't what we would say something that demonstrates knowledge. But let's look at a different question. What role does evaporation play? Well, this student has some sense about the water cycle and realizes that the water cycle might be important, and they've got some specific science knowledge that they are using to ask this question. But is this something that we can directly test out? It's kind of a vague question. We could probably refine that so that we could make it something that was investigatable. But simply saying what role does evaporation play is a little bit vague. It's much like saying, why is it green there? Is it evaporation? And it's not really productive enough. Here's a 4th question. How deep do roots go down into the groundwater? Well, clearly this person knows about groundwater. And could we figure out how deep the roots were going? Well, yeah, we could pull up plants and actually investigate that. So this is an investigatable question that demonstrates knowledge, and this is where we want to get all of our students moving towards when they start with questions that are simple, unbridled curiosity. So what I'd like you to do is, if you wrote down a few questions, try and categorize them into these different groups, and then try and see if you can improve a few of them. Revise and select, say, 2 questions that you would investigate, and I have them submit their questions to an online site, a form in Google that allows me to see all of their questions. And I might give them bonus points to determine which cross-cutting concept their question probes, depending upon how familiar your students are with cross-cutting concepts. So now, let's pretend that we've done that, and here is a post-it note, and a student has asked something about, is there some sort of rock layer that blocks the water? Well, I don't have a specific geologic map of this region, but I do know that in some cases faults can be involved in affecting the rock layers. So let's see, you've unlocked a new data set. I happen to have a fault data set, and let's take a look at that. Well, this is an example here of an oasis along a fault. You can see that it's long and straight. If you look at our oasis for comparison, you see some of these things are going one direction, some are going another direction. I'm not sure that this meets the criteria of being long and straight, so it doesn't look like a fault. But even, are there any faults in this area? Well, here there are faults nearby. Those are these red lines and black lines on this particular graphic. But our study area is in this little spot here on this geologic map, and it doesn't seem like those faults are anywhere near our study area. So probably not a good source of this explanation. All right, I have another question here from a student. Does it get greener when it rains more? You've unlocked a new data set. I happen to have some seasonal data, and let's take a look at that and see if that helps us. What I've done is I've gone into Google Earth, and Google Earth allows me to go back in time, and you can see different dates that I've gone back to, and there's not a lot of data, but there are some places where I have repeated measurements. Here are 2 measurements in March, and 2 measurements in October, 2 measurements in Novembers of 2009 and 2015, for example, and 2 examples in May. Now you'll see that Google Earth doesn't have a whole lot of data, so I can't compare March 2011 to May 2011. But I can take a look at this and see there's a little bit of variation from year to year, and when I look at the 2 panels side by side for a given month. And I can also ask the question, is there a time when it seems greenest? Well, it seems like maybe either May or October. Sometime between May and October seems greenest to me, and it seems least green here in March. Now, that makes a little bit more sense if you know something about the Tucson area, which actually experiences some monsoonal rains during the summer, unlike many parts of California where it rains much more often in the winter time. So this is consistent with more rainfall during these times, but the green areas look greener in the summer, and so do these bushes out here in the brown areas. So I'm not sure that we're getting a huge amount of information from looking at this seasonal data set. It doesn't tell us why the areas here in the green areas are different. So we need another thing. So somebody noticed here, and does the shape of the green areas have something to do with it? Now this question isn't specifically testable, but it does demonstrate that they observed something, and they are wondering about the shape, and maybe the shape is a little bit hard to see in what we were looking at before. So you've unlocked a new data set, higher resolution imagery data. We got our previous images from Google Maps, but Bing has a different data set that we can look at, and I think it's a little bit clearer actually. Take a look at this. Here's a road, here are some of these bushes, and here are our green spots. And now along the left margin of all of our green spots, except maybe this one, I see kind of a straight line. That's kind of interesting. Let's look at it from a different perspective. Bing allows us to see things in a bird's eye view, and here we are again. You can see those long straight lines there. They almost look artificial, say my students. I wonder what could be causing that. And here's a single one of those as well, and you can see that those long straight lines appear to be kind of little long straight hills. Well, that was intriguing. We might start having to discuss here, does this support or refute some of our models? Does this consistent with some of the ideas that people had, or do we want to change our models? So we could try changing our models, but I don't think we're ready to do that yet. I think we need to look at a few more questions and answers. So here's somebody that says, has it always been so lush and green? And this person, you've unlocked a new data set, long-term temporal history. Let's take a look at that. I went to another website. This one's called historicaerials.com, which allows us to get aerial photos over a much larger time span. And the only problem with them, of course, is they put this nice watermark across our images. But we're going to be able to step from 1958, where we're here in this area, where I don't really see any green spots. I just see these river channels, and there's the road that we were looking at. Here we are in 1966. Ooh, I'm starting to see those straight lines that we saw. 1967, wow, already by 1967, oh, sorry, I skipped over 1967, I have 1990 here. Okay, it took a while here, but by 1990, a few decades later, we're starting to see some lush vegetation in there, and then in 2013, we see it in color with the aerial photograph. Not much different, though. So what did we learn from that? What could have happened between 1958 and 1966? That seems kind of abrupt. I think we're starting to get some real serious evidence that these particular features were caused by humans. So what's going on? Well, we've got one more data set. You've unlocked a new data set where someone asks the question, is something different about the soil inside versus outside? And this data set is a video data set.
And it gets bigger and denser with more and more mulch deposit. Here's a massive accumulation of organic matter here. Now the soils are really rich in here. This is dark soil, damp, dark, and full of organic matter. Look at this stuff. And when we go down into the bottom land, it gets even better. This is a very special scene. No maintenance, 80 years of fertility accumulated by water, designed to infiltrate into this arid landscape and create that scene. Self-mulching, self-composting, soil creation. Look. Moist, crumbly. You couldn't make better soil than that. You couldn't. It's not possible. I'm going down 8 inches. Who needs compost? I feel so excited and hopeful. I feel so relieved. There are so many innocent people, little children out there suffering in dry lands, and they don't need to be. They just don't need to be. And they don't need to have these big debts to energy and consumption. This is nature facilitating its creative processes through good design. And we can teach, I could teach school children to do this. 5-year-olds, no problem at all.
Now I think we're ready to revise our model based upon all the new information we've got. And so we give our students some time to work on revising their models, drawing probably completely new models in many cases, because a lot of their first initial models weren't really very rich in this. And what should that model include? Well, a successful model for explaining this situation probably marries together 2 different classic textbook models, one from a life science textbook and one from an earth science textbook. We've got ecological succession, where soil is developing over time, the vegetation is starting off and getting richer and richer as we accumulate more and more organic matter in that area. And how come that's happening in this particular case? It's happening because there was a disruption to the water cycle caused by those berms, those little hill slopes that people built. How does that look? Well, as water runs along, it gets caught by that little hill, that little berm, and starts soaking into the water in one particular spot, leaving a lens of a little bit more groundwater. It stays moister a little bit longer in that spot, and that allows a little bit of vegetation to take root. And once that little bit of vegetation takes root, it grows and it dies, adding a little bit more organic matter to the soil. Now, the little bit of organic matter to the soil starts changing the way that water is absorbed and retained. And so you are having this organic matter interacting with the water cycle. As you add more organic material, you trap more and more water, which allows you to accumulate more and more vegetation, which dies and creates more and more soil. And we see the succession happening as those roots go down in there and pull out the groundwater. This is the result of a reinforcing feedback. And feedbacks are a big part of the NGSS high school understanding of cross-cutting concept 2, cause and effect. We turn cause and effect on its head here, basically, where what's the cause and what's the effect? Was it the plant growth that caused the absorption of water? Or was it the absorption of water that caused the plant growth? And this cycle is going around and around and around. Now, this is nothing new. This is what gardeners have known all along. This is why we mulch our beds, is to keep evaporation down, to allow rich, humusy organic matter to accumulate within our vegetation. And we can now point to that and maybe go out to our school garden and see the relationship between the oasis in the desert and what's going on right there in our garden bed. You might be wondering, well, which PEs did we address? Well, there's actually quite a few. There's two here that I'm going to highlight at the top. HSLS 2-5, develop a model to illustrate the role of photosynthesis and cellular respiration in the cycling of carbon among the biosphere, atmosphere, hydrosphere, and geosphere. Now, we have not developed a really rich understanding of the carbon cycle, nor have we talked much about photosynthesis and cellular respiration, but we're looking at one important piece of that cycle, where we're looking at how that organic matter is taking carbon out of the atmosphere and adding it into the soil. Now, within the Earth and space science realm, we have been analyzing geoscience data to make a claim that one change in Earth's surface can create feedbacks that cause changes to other Earth systems. And in this particular case, we had an example of the hydrosphere, the water cycle, causing a feedback with the biosphere and seeing how those two interact, and they do that through changes to the soil, which we would call the geosphere. So we've definitely done a nice job of looking at that. Have we been analyzing data? Not so much. We might need to make some changes to our lesson to extend it a little bit to emphasize some things that would allow our students to really fully accomplish these PEs. We might need to include some specific data showing the succession process. We might need to look at photosynthesis and respiration in a little bit more detail and include them explicitly in our models in order to satisfy these first two PEs. Now, these other PEs aren't covered quite as directly, but we do have a good foundation for jumping off into them. LS 2-3 is about cycling of matter in aerobic versus anaerobic conditions. And so we can basically extend our example of the cycling of matter there into those two specific conditions. We can also start putting some real numbers on things and perform mathematical representations to look at how biomass is moving from one part of the system to the other, and that would be LS 2-4. Again, we'd have to add other additional activities to our lessons in order to go there. This one here, evaluate claims, evidence, and reasoning that the complex interactions in an ecosystem maintain relatively consistent numbers and types of organisms in stable conditions, but changing conditions may result in a new ecosystem. Did we see any changing conditions? And did we see changes in the types of organisms that were there in those green areas? Absolutely. So in fact, actually, you might be able to move this one here up into the category of things that we actually did address. And lastly, developing a quantitative model to describe the cycling of carbon among the hydrosphere, atmosphere, geosphere, and biosphere. Again, we didn't include specific numbers, but that is something that we could do to modify this lesson to help extend it so that we were helping accomplish more of these performance expectations with our students if we had time. And if we don't, we stick with what we did, where we're covering parts of two performance expectations and really giving our students a rich experience with them.